Hello everybody. Today I want to show you how to analyze and play random NIM games well. You would need a little knowledge about what a game tree is, what a game digraph is, and about backward induction. Otherwise you will not be able to understand this analysis. So it's more an example about the tools, not really an introduction into it. So let me start by explaining the classical NIM game, which many of you might know. It is like this. We start with a number of stones, let's say n stones, and the two players alternate and remove one or two stones each. The first player facing an empty desk who cannot move anymore loses. This game is well known to many, and I guess you also might know how to play it, but let's try it out and see how to play it. So let's say we start with 7 stones, and let's say we can start, so we play against the computer, and then many of you will know how to play this correctly. You have to start removing 1 stone. The computer removes 1, we remove 2, computer removes 2, we remove 1, and we have 1. So let's play it again, and let's explain how this is done. So you have to move in such a way that you leave the desk with 3 and 6 or 9 and 12 stones. So in this case there are 7, so you have to go to 6. Computer does anything, you remove 1 stone to leave 3 of them. Computer does anything, you remove the rest and leave nothing. And you win again. So with 7 stones and you starting, you can always win. In this video I want to discuss a variant of NIM, which is called random NIM. And it is very similar to the previous one, except it contains some randomness. So again, we start with n stones. The players alternate and remove 1 or 2 stones. And the first player facing an empty desk loses. But the difference between the random NIM and the ordinary NIM is that between each of the players' moves, a stone can crumble randomly with probability p. So it's 1 stone is removed with probability p. And of course, depending on p, we get different games. With p equals 0, we get just the ordinary classical random NIM. Let's also try it out and play it. So let's try it out. We start with 7 stones, and let's say we try to play the same as before, at least initially. That means we remove 1 stone. Okay, nothing is removed randomly. Computer removes 2 stones. 1 stone is taken randomly, and we are facing 3 stones. What do we do now? Well, if we remove 1 stone, then certainly the computer player will be able to finish and will be able to win. If we remove 2 stones, we might be lucky that randomly this remaining stone crumbles, leaving the computer facing nothing and losing. So in this situation, we certainly should remove 2 stones. So let's see whether we get lucky. Nothing is removed. That means the computer can remove the final one and the computer wins. So you see already the difference. If we start with taking 1 stone, we, well, in this case, lose. So let's try it again. We remove 1 stone, nothing is removed. Computer removes 2 stones, nothing is removed. Now we have 4 stones. What do we do? Well, if we would remove 2 stones, then certainly the computer would be able to finish, whether or not one of the 2 stones is crumbling between or not. So 2 stones is not a good idea. Maybe we try to remove 1 stone. Then, okay, let's see. 1 stone. 1 stone is removed randomly. Computer, well, wins again. Let's try it again, just once more. Starting, removing 1. Removing 1, computer removes 1. The same situation as before. So again, certainly not a good idea to remove 2. I mean, 1 is also not safe, as we have seen before. But maybe we try. 1 removes nothing. Computer removes something. Randomly, nothing is removed. And you see, we can finish it and we can win at least once out of 3 times we have won using this strategy. So let's now go to the game digraph and see how to analyze this game and to find out how to play correctly in this situation. Let me start by analyzing random NIM 5, 1/3. So we have 5 stones, and between moves a stone is removed randomly or crumbles randomly with probability 1 over 3. You have to know that sequential games are usually analyzed using a game tree or a game digraph if you want to have it in a more condensed form. So in this case, I'm going to the game digraph of this game. What we have is we have vertices for n's moves. So n might face 5, 4, 3, 2, 1 or no stone. Then we have vertices corresponding to moves of bears, again facing 4, 3, 2, 1 or 0 stones. And we have the vertices corresponding to random moves in the middle, where we have the situation of one stone crumbling or not. The probabilities are shown here. So 2/3 nothing changes. We go from 4 to 4. And 1/3 the number of stones is removed randomly by 1. And of course we have usually two situations of these random moves. We can either have a random move where we have 3 stones and the next player would be bears, so this is this one here. Or we might have 3 stones, a random move, and the next human player playing is n. So that means we need two situations here. We have 2 random moves, 2 possible random moves with 3 stones. One where the next player is bears, one where the next player is n. As usual, we have to start at the end. It's backward induction, so we know the end positions. So no stones left, n supposed to move means n has lost, so the payoff for n is -1 and for bears it's 1. And the same of course in the other case, no stone left, bears supposed to move, payoff is 1 for n, n has 1 and -1 for bears. Now what we do is we want to get payoff labels for each one of these vertices on the digraph, and we move of course from right to left. We start with the 4 vertices on the right, like here. That is fairly simple and I don't really want to discuss this a lot. Whenever we have only one move out of a position, out of a vertex, then we just copy the corresponding payoff. So in this case we have there's only one option for the random move, nothing left, nothing can be removed. So we take these 2 payoffs and copy them here. The same here for this situation, we go here. The 2 payoffs, we copy them here. And here is n, 1 stone left, there's no choice for n. N has to do this one, and this yellow color indicates that is what n will do in this position. Remember, she cannot do anything than that. So that means we take these 2 payoffs, 1 and -1, and copy them here. And the same for bears here, only one option. So we have to go this way. We take the 2 payoffs and we copy them here. Next, what we want to do is we want to get the payoffs for this position. So we move a little further left. Now we have the typical situation of a random position, so a random move. And in random moves, backward induction means you have to take the expected value of the payoffs for this vertex. So we have 2 possibilities. Either no stone is removed with probability 2 over 3. You see the probability here on the gray arrow. And 1 stone removed is probability 1/3. Of course, the sum of these numbers must add up to 1. Now, what we do in this case is we calculate the expected value of the payoffs for n. Let me see. You see, we have 2 over 3, which is the probability for the first option to happen, times 1, which is a payoff for n. In this case, we have the product here. And we add 1 over 3, which is the probability for the second option, times -1. So again, the payoff for n in the second option. We do the calculation. 2 over 3 minus 1 over 3 is 1 over 3. So this 1 over 3 goes right here. We have to do the very same calculation for bears. You see it here. 2 over 3 times -1. So 2 over 3 times -1 plus 1 over 3 times 1 1 over 3 times 1 equals totally negative 1 over 3. So this negative 1 over 3 is a number which goes here. Expected value for Baz in this situation. We can do the corresponding calculation for this random position. We get payoffs of negative 1 over 3, comma 1 over 3. Again, first one is for n, second one is for Baz. The same kind of calculation, I don't really show it again. Next we look at this position. It's a human position, so in a human player position, the calculation is different. It's exactly the same procedure that you have done in sequential games without randomness. So what n does is she looks at the two options she has, removing one stone and arriving at a payoff of negative 1 over 3 for n, and removing two stones and arriving at a situation of a payoff of 1 for n. Now n of course focuses on the higher of these two values, which is a 1, and she goes for the 1, as you can see by the yellow color here, and the 1 is also copied there. Now it's important to understand that in this situation we don't do this calculation again for Baz because it's an n move. So what we do is we copy the whole black circled payoff for the position where n will aim to, and copy it here. So the black payoffs are just copied there. Next we do it for Baz here, the same procedure. Baz has two options, removing one stone, arriving at a payoff of negative 1 over 3, or removing two stones, arriving at a payoff of 1. So what will Baz do? Well, negative 1 over 3, 1, which one is a higher one? Well, she obviously goes for the 1. So the arrow points to the higher of the two outcomes for the possible positions you can go to. And again, we will copy the whole pair of payoffs there. So you see it here, the black circled payoffs, both of them are copied down here to negative 1 and 1. Next one is a random position again. So what do? We do the calculation as usual. So we have 2 over 3 times 1 plus 1 over 3 times 1. We get a 1. So this is a little silly calculation. So for this reason I omitted it. If we have two outcomes and both carry a payoff of 1 for n, of course the total outcome will also be a 1, and that's the same for the Baz position here. So this is some rather simple calculation. In principle it's the same calculation I showed before, but it's not so interesting. For this reason I kind of skip it and move to the next one. So here we go to n again. So what does n do? She focuses on the payoff here, negative 1, or the payoff there, negative 1 over 3. Which one is higher? Well, negative 1 over 3 is higher than negative 1. That means that is what she does. She goes to the negative 1 over 3, as you can see by the yellow color again, and she copies the whole pair, negative 1 over 3, 1 over 3 there. So keep in mind, we don't do this looking for the maximum twice. We do it only once, only for the corresponding player. For n, we look at the first entry. For Baz, we look at the second entry, and we copy the whole pair of payoffs to the corresponding position. Now the same for Baz, it's really symmetric. So Baz will certainly go here. I omitted the calculation because it's the same as it was before. Another random move, and a little more interesting than before. So what are the expected payoffs in this case? Well, we look at 2 over 3 and negative 1 over 3 and 1 over 3 and 1, and we do the calculation. 2 over 3 times negative 1 over 3 plus 1 over 3 times 1. So we get eventually a payoff of 1 over 9. We write it down here. And we have to do the very same calculation, but now for the blue, for Baz. So for random positions, you always have to do two calculations and always 2 times expected value. And again, of course, for 3 players, it would be 3 times, obviously. So for pairs, we look at 2 over 3 times 1 over 3 plus 1 over 3 times -1, and we get a payoff of -1 over 9. By the way, it's not a coincidence that these expected payoffs at every vertex here always add up to 0. It's a zero-sum game. So this will also happen between, that the expected payoffs at every position would add up to 0 in a zero-sum game. Okay, I skipped a few of these calculations. So again, another random move, another n moves here. So she removes 1 stone here in this situation. Beth moves here, she removes 1 stone. Again, why here? Because -1 over 9 is better than -1, so she certainly goes for the -1 over 9. And again, keep in mind this one is copied here because she goes there. Another random move, more complicated numbers for the calculation, but the calculations are exactly the same. Twice expected value calculations. And finally, an n move again. So which one is better? 5 over 27 or -1 over 9? Well, 5 over 27 is positive, so it's obviously the better choice. So we take the whole payoff pattern, 5 over 27, -5 over 27, and copy it here. And that means that the expectations for n in this game is 5 over 27. So n will more likely win the game than Baz. So the expectation is 5 over 27, which is about 1/5. So she will win more often than Baz. And of course, how do they play? Well, n will remove 1 stone initially. If n has 4 stones, she will remove 1 stone. If she has 3 stones, she will remove 2. With 2, she will of course remove 2 and win. And with 1, she will remove 2 and win as well. And you see for Baz, it's really symmetric. If Baz has 4 stones, removing 1. With Baz having 3 stones, removing 2. With 2 stones, removing 2. And with 1, removing the only remaining 1. Now this analysis and this game digraph can very easily be extended to a larger number of stones. We just extend it to the left. So here's a solution for the 7 stone version. And you can see the expectation for n starting with 7 stones is negative. So Baz will more likely win than n. But you can see also something else. The way we played it in the demonstration, removing 1 stone initially, is not the optimal one. So if you play it this way, then your expectation is -5 over 27. But if you play it correctly, removing 2 stones initially, your expectation goes up a little to -7 over 81. So you see, in this version, starting with 7 stones is not really good for the player. You will, on average, lose more than you win. And you should also, different to the ordinary classical NIM game, you should start by removing 2 stones. All right, thank you.